Good morning, everybody. I'm Clive Watkins. I'm the Director of Advancement at ASIJ, and this is our monthly elementary school Mustang Connect. Just to remind everybody, we started doing these sessions this year where we were doing these Mustang Connect sessions with the different division levels, just to update people on what's going on, also give a chance for some back and forth. We also have our 2030 sessions, which are generally where we bring in outside professionals who are talking about the world of education. And then we have our no value care sessions, which are generally our in-house professionals who are talking about things. And on that note of no value care sessions, just to let everyone know, there is one coming up on Monday, May 9th. From 1 to 2:30 in the afternoon, and it is Raising Healthy Kids in an Age of Dependence. You can see information about that on the gate. There's some pre-reading that's being suggested by our host for that. And on that timing of 1 to 2:30 in the afternoon, it's similar to this. We had a comment from Justin last time about the time of day, the amount of effort that my colleagues put into this work, and then the number of attendees we get. We realize it's not always the best time for people, but as we are doing right now, we are recording and we will make it available for people that they can watch it later. So if you enjoy the sessions, please do tell your friends about it, that they can watch the recording. This morning's session is about math, or maths, as we were debating is the subject. And I'm looking forward to hearing about this, but I'm going to turn it over to Mark to start with, to tell us more about this morning's session.
Yeah, thank you, Clive. This morning we have Leah Shai, Dr. Shai, working with us, and Randy Wilkinson, our elementary curriculum coordinator. The work that we're going to share today is really what a lot of parents ask. Why do we teach math the way we teach math? Why do we follow the Common Core? What's the background to this math craziness that when I want to work with my child at home, I really don't know how to help them? So we're going to we have experts from outside, from Stanford University. We have experts from inside. We have a high school teacher sharing her thoughts on the process. And we also have students, our experts in-house. Our students will be demonstrating their thinking in math throughout this session. So hopefully by the end of the session, you'll see multiple people talking about why and how. And then our next Mustang Connection, we will be sharing strategies you can support your child at home with. So this was part one of our math series, and our next one will be more of supporting your child at home. So good.
And when we share our definition of learning, it's not just learning in general as kind of an umbrella concept. We're really also thinking about it within the areas of the different subjects. So I'm going to read the definition of learning, and as I do, be thinking about what those words mean in the context of learning math or maths, depending on how you say it. Learning is a personal, lifelong process that leads to change, including the ability and willingness to adapt. It is driven by curiosity and motivation, occurring in a supportive environment, rich in engagement, social interaction, and feedback. Learning is constructed in authentic contexts and results in the development of new understandings and skills for all learners. And you'll notice in that description, there wasn't anything about learning happening on time tests or by memorizing exact answers and always getting things right. So our approach to learning math, helping our students learn math, might be different than the approach that was used for us when we were learning math. So we hope that you will also have an open mind as we go forward in our presentation.
We also, part of our strategic design framework, we talk a lot about deep learning. And so this is the focus where we ask, deep learning focuses on asking the right questions rather than having the right answer. And that's some of the demonstration we're going to show today. We're not always looking for the exact answer to a problem, but we're looking for the thinking behind the answer. And you'll see that through some of the practices we share today. And that with the focus on process and authentic problem solving, student engagement, and transformational learning experiences that are mindful of culture, identity, ability, and foster creativity, adaptability, and iteration. So it's a lot of a trial and area and back and forth thinking through the process. Along with that, we have a portrait of learner competencies, and you will see, I hope, as we go through this, how our competencies are embedded in our math practices, right? So we have our math practice, making sense and persevering, using reasoning to solve problems, constructing visible arguments, modeling, using tools strategically, tend to precision, and use of structures to support your learning. If you look at the mindset portrait, mindset, communication, creativity, critical thinking, collaboration, and global citizenship, most of those are found within the math practices, and students are engaged in that throughout the day with math.
Okay, so we're going to open with a quick introduction video that kind of gives you an overview of maybe how the way you learn math looks differently than the way your children are learning math now. It opens with an analogy about using recipes to cook, and then being a cook, being a baker, and being able to manipulate the ingredients to prepare, creative, unique dishes and desserts. So let's have a look.
Hey, Randy, is there meant to be audio with this?
You can't hear the audio?
No.
Not at all.
I can hear the audio in my ears. Let's see.
While you're figuring that out, let me just remind people that we do have the Q&A function here. It's not anonymous, so if you do ask a question, your name will be there. But if you have any questions at any time, such as why can't I hear the audio? Just kidding. Go ahead and put it in the Q&A function there. And if you see your question that's already been asked, you can just click on it, and it'll move it up in the screen.
So tell me how this sounds. It might just be recording from my speakers or my computer.
Certainly will.
So math in some ways is like baking, and math used to be taught as a recipe, as a series of steps you do, and then you get a result. And what you understand if you're a cook or a baker is that you add things in certain proportions for a reason, and that your cake has to have this percentage of fats to this percentage of flour in order to work. And what Common Core tries to do is to do the same thing with math, sort of developing what they call number sense. And number sense is understanding more or less why we do the things we do. Common Core is taught in a way that most people over 20 don't recognize.
We find ourselves tearing out our hair at the new math.
It's the same thing I do when I get a check at a restaurant, draw a bunch of shapes and tell the waitress to find my error.
Parents taking to Twitter, posting unbelievably complicated homework assignments.
These math problems circulate that just seem really nonsensical, which is really frustrating. If you have a kid who has this simple problem that looks like it's being made way too complex for no reason, it's totally understandable why people would say, this recipe that I learned is the quick and easy way to do it. Why aren't they just teaching kids to do that? So for example, we all learned to borrow when we subtracted, but this doesn't really show you what you're doing. It doesn't really show you what borrowing is. And so one of the ways the Common Core tries to explain this is with a number line, because subtraction is really about finding the distance between two numbers. You start with the number you're subtracting, and you take little hops up to a more round number. So you go 10 between 90 and 100. So you've sort of broken down this distance, and you add these numbers together. There's another method called the counting up method, and this is also for subtraction. Count up from 38 to 40. Then from 40, you want to go up to the next big round number, which is 100. Then you need to go from 100 to 300, and then from 300 to 325. So that's the distance between 38 and 325, are these numbers that I've circled. You get this idea in your head that numbers are flexible things made up of other numbers. 40 is a 38 and a 2. The standard algorithm is the easy and quick way to do it. Students absolutely still have to learn to do it that way. But the idea is that this gives them a better understanding of what they're doing, and that there are a lot of ways to do this. There isn't just one right way to find the solution to a math problem. You read through the standards and they seem like really reasonable, good ideas. The most important thing is how they're taught. Teachers understanding what's expected of them, having the resources to teach it well, because otherwise you do end up with math problems that don't seem to make any sense at all. And in some cases, that's just the parents not understanding it. In some cases, it probably is a bad lesson plan, a bad textbook, a teacher who doesn't quite understand what they're supposed to do differently now. There are definitely bumps in the road.
Okay, so in our classrooms, in our math instruction, we take a balanced approach. And just like you saw in that video, it's really important that kids are able to visualize and make models of the ways that they're able to compose numbers and decompose numbers and think flexibly when using those numbers. This is one of the steps to get to quicker ways of solving problems like those standard algorithms. But it's really important that they can visualize what's happening in their head or with math manipulatives in the classroom. Another part of the balanced approach is that model making helps to build the conceptual understanding. And this is where that number sense comes in. Just knowing what a number in that tens place means, and then what it means to subtract. These are sort of big concepts that we take for granted. So once those are in place in our math workshops, like that video said, there's still a place for standard algorithms, equations, but it's really important to know why those numbers are doing that before we get to this step. And this is how we sort of quicken it. But in order to be flexible and to be able to apply this to real world problems, we need to have an understanding of the models and the conceptual understanding as well as this. So all together is what our math workshops look like.
So now we're going to hear from a series of experts a little bit more about this idea of number sense that video introduced. And as we go through these different examples from the experts, you'll hear those three different parts, or you'll see those three different parts of the balanced approach represented in different ways. So our first expert is Dr. Joe Bowler, who is a professor at Stanford.
Hi, my name is Joe Bowler, and I'm a professor at Stanford. So what is number sense? Let's think about a problem. Let's think about 18 times 5. A student with number sense could solve this in many ways. For example, they might say, I know 20 times 5 is 100, and I know 2 times 5 is 10, and I'll take 10 away from 100, which gives me 90. We can visually represent that, and visual connections are really important for our brain. So what would that look like? If I drew 18 times 5 as a rectangle like this, we could represent 20 times 5 by saying it would be a slightly bigger rectangle, and we'd subtract this blue part. Another way to think about 18 times 5 is to say it's actually equivalent to 9 times 10. And the visual representation of 9 times 10 is kind of interesting. If our 18 times 5 rectangle looks like this, then our 9 times 10 rectangle would look like this. And that 9 times 10 rectangle has the same area as the 18 times 5 rectangle. A third way I might solve this is to say, well, I know 9 times 5 is 45, and I can do that twice to give me my 18 times 5. And that visual would look like this. There's our 18 times 5 rectangle, and this time I worked out 9 times 5 and 9 times 5. And there we have those two rectangles. A fourth way to solve this is somebody might say that they want to break up the 18 to work out 10 times 5 and then 8 times 5 and add those solutions together. And the visual of that is, if this is our 18 times 5 rectangle, then we can find our 10 times 5 and 8 times 5 rectangles, and they would look something like this. Another way, a fifth way of solving it, is not to think of 5 18s, but to break that up and to think of 2 18s are 36, and then we have another 2 18s are 36, and add on a single 18 to give us 90. And that visual looks a little different to our others. So if we have our 18 times 5 rectangle, this time we've broken up the 5 into a 2 times 5. Can you find different ways of solving 12 times 9, both numerically and visually? The variety of methods we see is part of the beauty and creativity in maths. All problems can be solved in different ways, and we should embrace that. Number flexibility, being able to work with numbers and see what they are made of and combine them in different ways, is an important part of number sense. If you'd like to see and learn more, come to UCubed.
So in that example, you could see the representational understanding by the actual rectangles and how they were shown, and also the conceptual understanding in the ways that the number was broken down, so it could be done in different ways. Our next expert is a first grade expert in one of our classes here, and she's going to talk through her representational understanding, which you'll see in some of these petals, as well as the conceptual understanding. So these things combined together are what she's going to describe in her number talk.
Hi everyone, this is my math flower, and I did it in many different ways. So what I do is kind of, so what I did was do in many different ways. So this is my number I made, 47. 47 is like, because in your birthday you'll become 40, so I put 40 here. And after this I'll become 7, so I made 47. Number 1 is number bond. You put parts of it, 40 and 7 equals 47. Number 2, coins. So what I did here is like 1, 2, 3, 4 of these 10 coins, and 7 of these 1 coins. 1, 2, 3, 4, 5, 6, 7. 47. Now this is our equation. 40 plus 7 equals 47. Now I did this a bit opposite. 7 plus 40 equals 47. And then there's a few more left, is place value. So this is the tens place, and this is the ones place. Now this one's quick draw. You may not see these look like tally marks, but these long lines represent tens, and these little X's represent ones. Number line is 40, you jump to 7, and then it's 47. So this is how it works, okay? And that's all it. Bye.
I think we need that person moderating rather than me. That was excellent.
I'll get on that, Clive. You might get what you asked for. But as you can see, there's a ton of creativity and beauty in how she described the number 47, way more probably than any of us when we were 6 or 7 years old were ever asked to explain. But with that foundation of number sense, as that student gets to harder problems and there's more complexity, she's going to be able to use those numbers in new and different ways to be able to solve those problems. And the next expert we have is a second grader. So now we're up 1 grade level, and we're not going to see the representational understanding here, but we will see the conceptual understanding combined with the computational and procedural understanding. So now we're going to 2 different kind of circles from those 3 concentric, or those 3 overlapping circles that Randy showed earlier in our balanced approach. This is a second grader talking about a subtraction strategy.
Hello, we will be solving the problem 163 minus 73. We will be using a place value chart. We will start by drawing the place value chart out. We add a H for hundreds, a T for tens, and an O for ones. This is because the hundreds go here, the tens go here, and the ones go here. We will draw the 136 because it is subtracted, so we only draw the biggest number. We will draw a tiny square for the 100, 3 sticks for the 30, and 6 tiny circles for the 6. Now we'll subtract 73. A tip is to always start with the ones. We subtract 3 from the 6, which is 3. We need to subtract 7 tens, but there aren't enough tens to subtract, so we regroup. Cross up 100 and bring 10 sticks. Now you can subtract 7 tens, so cross up 7 tens. Now there are 1, 2, 3, 4, 5, 6 tens left. And there are no hundreds, so it is 63. Thank you. Bye.
So I apologize, I misspoke when I said that you wouldn't see the representational part, but you did. She drew it. And if you've seen kindergarten, first grade classrooms, they'll often use actual blocks, right? So when it's one item, it's a tiny little cube. And when it's 10, there are 10 cubes stuck together into kind of a longer rod. And then when it's 100, there are 10 of those rods stuck together onto like a flat piece with 100. So the students learn after touching them and using them to represent them in this kind of way on their drawing. Our next expert that we're going to hear from is one of our high school teachers here at ASIJ, and she's going to be talking about how the number sense foundation that they're building now, how important it is when they get into much higher level mathematical thinking.
Building conceptual understanding in math when children are young gives them a greater sense of numbers. It develops their number sense. The more they understand how and why numbers work the way they do, the more flexibility they're going to have when they're working with numbers and mathematics. When students are young and they're first learning mathematics and mathematical procedures, it's really easy to memorize a bunch of steps and tricks in order to get to a solution without really having an understanding of how or why the numbers work the way they do. But as children get older and the mathematics gets more harder and there are more and more formulas for them to learn, they can't possibly memorize all these steps. The more children understand how numbers work and the more they realize that there's a variety of ways to solve problems, the more willing I think that they'll be and are to take risks and to try new and different strategies and to be wrong. If you simply memorize the steps, you really only learn one strategy and you really start to think about mathematics as either right or wrong with one possible solution. Also, if you're just memorizing steps and procedures, it's harder for you to understand if answers really make sense in the context of a problem. The children I see who rely on memorization start to in high school get all their rules mixed up and confused. And then really when they see an answer, they have no conceptual understanding of why that answer is right or wrong. But when students have number sense, they're able to develop their own strategies and their own ways to solve problems. And they're making sense of the mathematics on their own. And they're able to see how and why those mathematical procedures work. When kids are good in math and they're passionate about mathematics, I think it's especially important that we allow them to do deep dives into mathematics that's developmentally appropriate for them in the mathematics that they're learning in their class. When I was in elementary school, it was common practice when someone was really good at math to just jump them ahead in the math curriculum. And the danger when you do that is that children are skipping over those conceptual understandings. And the goal shouldn't be to get through the math curriculum faster. The goal should be to understand how numbers work together and to develop a love of numbers and to be able to see the beauty in mathematics. Conceptual understanding in mathematics pays off so much when students are in high school because they have an increasingly better understanding of mathematics and they have the skills that they need in order to succeed.
Okay, so Trisha mentioned both fun and deep dives. So we're going to show you a problem where we can kind of demonstrate, kind of like Joe Bowler did actually with her little pyramids as well, sort of what it looks like to tackle an open-ended problem. There's multiple ways you can solve this. The benefit of this problem too is there aren't any numbers, so there's no right answer. So in a classroom and a workshop approach, this is going to have all their creativity bubbling up and their collaboration, and it's going to inspire kind of debate around the mathematics, and we're going to be okay with being wrong and evolving our thinking. So we have a problem here, and we're going to show you 3 different ways that we've looked at it and solved it. So this is the shape, and the question is, what fraction of the shape appears to be shaded? So we're going to hear from Leah first, how she thought of this.
Clive, do you have any suggestions on how you'd solve this problem?
Oh.
I do, but I think I should let you guys go ahead. I don't want to give the answer away.
Maybe afterwards. We'll come
All right.
back to you.
Okay, Clive, well, you weren't going to give the answer away. The actual prompt said what appears to be shaded. So I'm not going to worry quite so much. My answer may or may not be correct, but I think I have some pretty good thinking of how I would tackle this. So I looked at that shape that actually is a pentagon. There are 5 sides, which is harder to kind of calculate and figure out. But I'm thinking if I can look at the area of that shape and then compare that to sort of the area of the whole square, then I'm going to be able to think about the fraction. So I took that pentagon shape and I divided it into 2 easier to deal with shapes, a triangle and a rectangle. So if I first look at that triangle portion, I'm going to start there just because it's the biggest one. I can roughly see there are 3 columns that look to be even. So that's thirds. But then visually, it appears to be that there are also 3 rows that would be equal. And it happens that that diagonal line kind of intersects right there. And so it looks like to me there are 9 equal squares. And then with that diagonal line cutting right straight through that middle square, that would be like 18 triangles if I cut them all up. Or it's half of one of those 9s. So I think the triangle portion that's sort of outlined in red is like the equivalent of 1/18 of the whole shape. And now I'm going to look to try to figure out what's the area of that rectangle, which is much smaller. And so I'm going to go back visually to the 9 squares that I made. And then within those 9 squares, it looks like that rectangle is about 1/4 of one of those squares. So it's 1/4 of 1/9 of the whole shape. So that would be 1/36. So my triangle is about 1/18 and the rectangle is 1/36. And so when I add those up, because I know that there are 2 18s and 36, so I would need 236 plus my 136, I have 336, and that reduces down to 1/12. So I think it's about 1/12 of the entire shape that is shaded there. And I remember doing a problem similar to this on a GRE. Like it actually asked me to put the numbers in. So it wasn't the flexibility of thinking, but it's a real skill. This isn't just totally like out there. If you've ever had to like tile a bathroom floor and you have to go around strange shapes, like you really do need to think flexibly. So that's how I would have done this.
That's exactly what I was going to say, but could I ask Ryan's question here? I'm not sure that you get to it later in the presentation, so you probably do, but let me ask it here anyway. Ryan's asking very legitimate question. Big fan of numbers and math. However, I have had issues in the past working with our son on math homework where it was difficult to help him do his math the way it was done in class, since that way is different than the way that we learned. How do you recommend handling this type of situation as a parent? He's tried Googling to try to understand what might have been going on in the class, but it doesn't always help how to do it. So how should us old-timey parents help kids who are doing it this way?
Yeah, I can take that one on. You know, that's a step where if your child comes home with math that they don't understand how to do, the best thing is to refer it back to the teacher so the teacher can re-explain it to them in the model of which they're using to solve the problem, right? So instead of trying to figure it out yourselves and getting frustrated with the way in which math is being done, it's really important for the teacher to understand that when that child left the classroom, they didn't understand how to solve the problem. And for them to go back to the teacher to get some reinforcement of the steps of the model of which they're trying to use to learn how to do the math. And also, this is kind of part 1 of a 2-part series.
And our next Mustang Connection in May, we're planning to focus more on direct specific things that you can do at home as a parent to help with math. So today we're focusing on kind of the background of how we teach math, the approach, the general philosophy behind it. And then in May, we'll get into more specifics to help you in those as well.
I think one of the important things that you said in there, Mark, was just the recognition by the parent, if not the student, that the student doesn't understand what they have been learning in class, and to share that with the teacher so that the teacher's aware of that also. So that's one.
Clive, it's really important that, homework isn't new learning. Homework is a reinforcement of the learning that took place during the course of the day or in the classroom. And so if a child is going home and they really don't understand how to do something, it's going to benefit both the teacher and the student for the parent to let the teacher know that there was a problem. That's really going to be a big help. It's a good question.
Let's see if Mark understood the assignment.
Yeah, so when I looked at the problem, I noticed that the squares were partitioned in thirds, or in 3 pieces at the top. And so I took it and I remeasured it, and I said, okay, so if it can break up into 3, how many rows of 3 can I make? And I found that there are 4 rows of 3 or 12ths. So I broke up the entire square into 12ths. And since it had already been partitioned in half by that horizontal line, I then just looked at the shapes itself, and I used a visual way to solve this problem. And I said, oh, I see that shaded part, that triangle on the bottom left might fit in the triangle that's missing in the top right. And just by visually manipulating, my prediction is it's very similar to Leah, that it's 1/12, because the colored shaded area is 1/12 of the whole. And so I did mine without really any numbers at all, and tried to solve it the same way as Leah did. Mine a little bit simpler.
No comment. No, just kidding. For this one, thinking again with both Mark and Leah's first strategy of that partitioning. So we've got 3 columns in thirds, and then building on my understanding of symmetry, that middle one is about half, because there's that same shape at the top as there is on the bottom. So then 1/2 of that 1/3 is 1/6 of the whole. So that's my theory on what the answer is. Just a little different. But as long as you just saw, all of us can defend our answer. If this were in a math class, we might talk a little bit further and ask questions and maybe put numbers to it and see if our methods hold up.
So this, again, it really relates to our portrait of a learner in the communication and critical thinking. Each of us have our own thoughts on how we would solve it. We need to share it. We need to really enforce how and why we have the answer that we have, and defend it. And that really, the communication and critical thinking are essential for solving that problem and to sharing your answers with others. In the next slide, we have a 3rd grade class, and what they're going to be doing is very similar. They've been given a problem, and within that problem, they're up at the board and they're defending their answers, and they're sharing their answers in a number talk to peers in the classroom. So have a look and listen. It's a short clip, but it really kind of shows you some of the activities that are taking place in class, where students have to share their answer and defend why they got and how they got their answer.
So I'll skip forward to the 3rd grade one, and then we'll come back here.
Yep.
Okay.
We got it. What fractions are they showing? Can you read the fractions? Oh, okay. Wait, no, this is not a fraction.
So in that, you hear some of the students going back and forth explaining, and then someone saying, oh, no, that's not right. That's not the same fraction. And that's a lot of the work that the students will be doing in school throughout their elementary years. Having an answer, defending their answer, sharing it in a visual model, so that they can represent their answer to others. And that's taking place quite a bit. Our next presenter is Graham Fletcher, and he's going to talk a little bit about how fractions, how the development of fraction understanding goes from first grade to third grade. We're just going to go all the way to third grade. We've kind of cut it past at third grade so people can understand.
Fractions. The very sound of the word, well, it kind of freaks most of us out. So here, I'm going to take a stab at explaining the progression of fractions. And it begins in first grade. And it starts with a crazy word, partition. And I think that students should be able to use that word as well. So in first grade, students should be able to partition squares and rectangles into halves and quarters, which can also be represented or called fourths. The vocabulary development here is the biggest piece in first grade. So they could also say a quarter of, a fourth of, or a half of. In second grade, students build on their understanding of halves, quarters, and fourths, and they're introduced to the idea of thirds. Again, they should be using that term, thirds or a third of. When students leave second grade, a big piece of understanding they should leave with is so even though shapes can appear different, they actually can have the same size. So this brings us to third grade. It's a really big year for the development of fractions because here students are beginning to really truly develop that meaning of a fraction. And it's the first time that students see fractions written as a symbol. So even though we're talking about symbols, we really need to place our emphasis as teachers on the visual representation of fractions. So how can we do that? Well, one way we can do that is by creating a length model. Here you see that we've taken a strip of paper and folded it up into 4 parts. Another way, which isn't really explored in third grade, is the use of a set model. Here in this set model, you can see that 3/4 of the bears are green. And the last way that we can represent fractions is one that I think we're all pretty much familiar with, and that's the area model. Here, 3/4 of our square is yellow. As students are building this understanding, we need to make a connection back to their understanding of what they have with whole numbers. So just as whole numbers, take for example, this number 4 is built from units of 1, fractions, in this case 3/4, is built from 3 1/4, a fourth plus a fourth plus a fourth. Big understanding here. Let's go back to that length model. Well, that length model is a really powerful tool because it helps build students' understanding, which can also be done through a number line. Here's another number line. What number is the question mark? Here, let me help. Wait a minute, that's greater than 1. Well, in third grade, students need to see that fractions can also represent numbers greater than 1. It's the sum of unit fractions. So we might want to get students to begin counting with fractions: 1/3, 2/3, 1, 4/3, 5/3, 2. Let's get our students counting by fractions.
Okay, so that was a really great representation of sort of what we mean by building students' conceptual understandings through representations of the numbers and breaking apart numbers and putting them back together. Something else that's interesting is a lot of kids have a misunderstanding that the equal sign means this is where the answer goes. And through work like that, we build an understanding that it's actually a mathematical symbol that means, you know, they're both equal on each side. So things like that, you know, a procedural recipe way only without, you know, the conceptual and representation models alongside it, they won't know what's happening. And then, like Trisha mentioned, over time, it's really just too difficult to remember all those procedures and those algorithms. So having that conceptual understanding is how we, you know, have mathematicians.
One of the resources as a school that we've focused on is Mathematical Mindset by Jo Boaler. It works closely with Carol Dweck, which if you ever heard the book of Growth Mindset, they're really interrelated. How do we build our mind to become more growth oriented? How do we help students understand that when you make mistakes, your mind, your brain grows? And it really emphasizes the potential of growing mathematicians, and that all students, everyone, has a chance to be really strong in mathematics. And so as a school, we read this book. As an elementary school, we've done some college work with her. We did courses with her a few years back, but it really builds the capacity for the teachers to understand the math, because most of our teachers were taught the way you were taught in math. And so we had to be retaught on how to teach math to this more understanding, conceptual understanding, and in number sense way. It's an excellent resource. And Carol's going to share a little bit about that growth mindset in mathematics in this next little clip.
So how many people here, let's get a show of hands, have ever been given the idea that they're not a math person, or that they can't go on to the next level of math, they haven't got the brains for it? Let's see a show of hands. So quite a few of us. And I'm here to tell you that idea is completely wrong. It is disproven by the brain science, but it is fueled by a single myth that's out there in our society that's very strong and very dangerous. And the myth is that there's such a thing as a math brain, that you're born with one or you're not. We don't believe this about other subjects. We don't think we're born with a history brain or a physics brain. We think you have to learn those. But with math, people, students believe it, teachers believe it, parents believe it. And until we change that single myth, we will continue to have widespread underachievement in this country. Carol Dweck's research on mindset has shown us that if you believe in your unlimited potential, you will achieve at higher levels in maths and in life. And an incredible study on mistakes showed this very strongly. So Jason Moser and his colleagues actually found from MRI scans that your brain grows when you make a mistake in maths. Fantastic. When you make a mistake, synapses fire in the brain. And in fact, in their MRI scans, they found that when people made a mistake, synapses fired. When they got work correct, less synapses fired. So making mistakes is really good. And we want students to know this, but they found something else that was pretty incredible. This image shows you the voltage maps of people's brains. And what you can see here is that people with a growth mindset who believed that they had unlimited potential, they could learn anything, when they made a mistake, their brains grew more than the people who didn't believe that they could learn anything. So this shows us something that brain scientists have known for a long time, that our cognition and what we learn is linked to our beliefs and to our feelings. And this is important for all of us, not just kids in math classrooms. If you go into a difficult situation or a challenging situation and you think to yourself, I can do this, I'm going to do it, and you mess up or fail, your brain will grow and more and react differently than if you go into that situation thinking, I don't think I can do this. So it's really important that we change the messages kids get in classrooms. We know that anybody can grow their brain, and brains are so plastic to learn any level of maths. We have to get this out to kids. They have to know that mistakes are really good. But maths classrooms have to change in a lot of ways. It's not just about changing messages for kids. We have to fundamentally change what happens in classrooms. And we want kids to have a growth mindset, to believe that they can grow and learn anything. But it's very difficult to have a growth mindset in maths if you're constantly given short, closed questions that you get right or wrong. Those questions themselves transmit fixed messages about math, that you can do it or you can't. So we have to open up maths questions so that there's space inside them for learning. And I want to give you an example now. We're actually going to ask you to think about some maths with me. So this is a fairly typical problem that's given out in schools, and I want you to think about it a bit differently. So we have 3 cases of squares, and in case 2, there's more squares than in case 1, and in case 3, there's even more. And often this is given out with the question, how many squares would there be in case 100 or case n? But I want you to think of a different question now. I want you to think without any numbers at all, or without any algebra. I want you to think entirely visually. And I want you to think about, where do you see the extra squares? If there are more squares in case 2 than case 1, where are they? So if we were in a classroom, I'd give you a long time to think about this, but In the interest of time, I'm going to show you some different ways people think about this. And I've given this problem to many different people. And I think it was my undergrads at Stanford who said to me, or one of them said to me, oh, I see it like raindrops, where raindrops come down on the top. So it's like an outer layer that grows new each time. It was also my undergrads who said, oh no, I see it more like a bowling alley. You get an extra row, like a row of Skittles that comes in at the bottom. Very different way of seeing the growth. It was a teacher, I remember, who said to me, it was like a volcano. The center goes up and then the lava comes out. It was another teacher who said, oh no, it's like the parting of the Red Sea. The shape separates and there's a duplication with an extra center. And I remember this this one as well. Some people see it as triangles. They see the outside growing as an outside triangle. And then it was a teacher in New Mexico who said to me, oh, it's like Wayne's World. Stairway to heaven, access denied. And then we have this way of seeing it. If you move the squares, which you always can, and you rearrange the shape a bit, you'll see that it actually grows as squares. So this is what I want to illustrate with this question. When it's given out in maths classrooms, and this isn't the worst of questions, it's given out with a question of how many, and kids count. So they'll say in the first case there's 4, in the second there's 9. They might stare at that column of numbers for a long time and say, if you add 1 to the case number each time and square it, then you get the total number of squares. But when we give it to students and teachers, high school teachers, and I'll say to them when they've done this, so why is that squared, do you think? Why do you see that squared function? They'll say, no idea. So this is why it's squared. The function grows as a square, and you see that squaring in the algebraic representation. So when we give these problems to students, we give them the visual question. We ask them how they see it. They have these rich discussions, and they also reach deeper understandings about a really important part of mathematics. So we actually need a revolution in maths classrooms. We need to change a lot of things. And part of the reason we need to change so much is because research on maths teaching and learning is not getting into schools and classrooms. And I'm going to give you a stunning example now. So this
All right, so hopefully we have helped you understand how our balanced approach with representational thinking, conceptual thinking, and then procedural and computational thinking are developing our mathematicians to be open and flexible, creative, and growth focused. And so with those in mind, can you add to the chat and just fill in these blanks, the sentence stems. I used to think, and now I think. So we're hoping that we can see some evidence of, yeah, your thinking has changed a little bit or grown a little bit around math and the way we're learning it.
Hey, Randy, while people are thinking what they might type in there, let me ask you Yuki's question that's been here. If there's a textbook for math at school, parents could also know how the kids are going about learning math. Also, the kids could review or see what's coming next. So why doesn't the school use any sort of textbook?
Yeah, I can get into that, and you guys can jump in a little bit beyond that. So we see textbooks as a tool. And what happens when people or schools use a textbook? It becomes the program, it becomes the curriculum. So it's like you turn the page. So the teacher says, oh, lesson 1, we finished. Let's go on to lesson 2. We finished. We go on to lesson 3. We finish. And it's that progression through the book. By the end of the year, we want to start. By the beginning of the year, we start on page 1. End of the year, we end up on page 300. We're finished the curriculum, right? And we want to go deeper than that. And so as a school, we do have a resource. It's Eureka Math. It's a resource we purchased several years ago. It goes in that cycle of lesson to lesson, but we know that students are all in different places. And if we just follow a book, those students that already have the skills, already have mastered their things, would be just doing things because that's the turn the page method, and we're only supporting what's left in the book versus the students in front of the class. And so as teachers, they have that as a tool. And as a parent, you'll see some of those practice sheets going home for students. But as a school, we don't use it as an everyday, let's turn the page, because they're pulling from so many different resources to help meet the needs of our kids. We have students at all different levels within the classroom, and the plan is to support all those learners and differentiate within their instruction.
So if I could sort of paraphrase sort of Ryan and Yuki's question, do we provide parents with any sort of resources to help them to understand the sort of math that is being learned right now? I mean, this is a great resource right here, but are there any other things that we can give them?
Yeah, you know, and this is something I will follow up with our teachers. In every unit, there is a parent guide that could be going home or should be going home to the parents to kind of help give some heads up as to what the learning of that unit is. Now, as I said, students will be at different places with that, so it doesn't go page to page with the learning, but the overarching concepts are in that parent guide, and we will double check them, see if those are going home as they should be.
Clive, can I just add on to that too? If you think about the example problem that the three of us talked out with the fractions and what portion of the shape was shaded, if a teacher were to give this question and then to hear we're only 3 students in the class, as you listened to each of us explain our thinking, you probably could see a little bit into kind of our heads as to what we were understanding and maybe what we might be misunderstanding and maybe what kind of our next step would be. And the next step for me in my conceptual understanding of fractions might be different than what Randy's was or different than what Mark's was. So if we had a textbook and we all had to go to the next thing, the 3 of us wouldn't be getting the next step of learning that we need. So these kind of open-ended questions are also really great ways for teachers to be able to understand their students as individual thinkers and learners, to be able to target kind of what's the next step of instruction. So there often are small groups working on open-ended problems that are going to be targeting more what they need instead of everybody in the class having the same textbook, doing the same next thing as they go through.
Yeah. You know, I'm sorry, we have somebody who's Ryan has put in his thing. I used to think, let me read it. I haven't read it yet. I used to also think there were math people, but now over the years, I think I was wrong. As a side note, I really appreciate this way of thinking about math. I was always labeled as a math-oriented person, and that ended up hurting my potential and focus in other non-math also things. And I would agree with Ryan on this. It was something that Randy had said earlier that, you know, my method of learning math was to learn, here's the way you do this, not understand why we do it that way, but here's the formula for doing this. And you're absolutely right that the more you go along and you have all these other subjects at the same time, you get overwhelmed by these formulas for doing things. You have to memorize these formulas as opposed to understanding why they do that. I would also throw out there, I know we're not talking about science at the moment, but I know one thing that's stuck in my head from science class, because I had to memorize it, was the table of elements. You know, it's a hydrogen, helium, lithium, and I did it by just memorizing the first letters of those things, but I had no concept of why, like why are they organized this way in this table? I still don't. Maybe I need to go back and do that. But I would agree with Ryan's comment there.
It was really interesting. About 6 years ago, we had some consultants come to school and they were working with our kids, and I sat in the high school session. It was called a Fishbowl. So they put a bunch of high school students in the middle and everyone on the outside is listening to a conversation about learning, right? And these high school students were talking about their experience at ASIJ and how they had a recipe for doing well at school, which was cramming, studying, memorizing for the assessment, and then forgetting about it until the next one. And that whole process of short-term memory, memorization to do well on a test, and not ever really understanding what the purpose and the connections to the learning they were doing. And that's really the big shift we're trying to get away from. We're trying to move through the process of learning because you want to learn, and you're engaged in that learning, and you understand why and how you're learning what you're learning. And so that's a big shift as a school, and an important shift, I think, for all our kids.
What it reminds me of, we've had a math consultant come, and we've, as elementary all the way through high school, taken some classes all together. And the math teachers in secondary, arguably the ones probably labeled with math minds, we'd be given a problem, an open-ended real life problem. And the way that first grade teachers, second grade teachers can simplify and model a very easy answer, whereas then the high school or middle school, they're trying to use their equations and making it very difficult because they don't have the practice often with, just distilling out what is the problem asking, what does it look like? So that's always fun.
I'm not sure if you guys are done with your presentation, because I wanted to throw in something here, that one of the things I had heard over the years, that I'm sure others have heard, is, oh, kids in Asia are very good at math. And why is that? And a couple of the reasons that I had heard for that is language. So in English, if you get to 10, all of a sudden we're 11 and 12 and 13. Whereas if you even look at Japanese, you get to 10 and 11. So ju-ichi. So 10, 10-1, 10-2, 10-3, the way that the language approaches the counting, and then also use of abacus as a thing for doing that, which sort of mimics some of the examples you've been giving. I know we don't have time to go into that, but I just wanted to throw it out there. Have you guys heard any of that sort of?
Yeah, and both of those things are examples of those three circles of the balanced approach, right? That an abacus is a representational way of thinking about numbers. And the language has built into it a certain amount of conceptual understanding. If the way you say the name of the number is 2 10s and 7, 27, that conceptual understanding is built in. English doesn't have that conceptual understanding built in, but that's one of the reasons that when we saw the first grader describing the flower, we want to make sure she understands that, because 47 by itself doesn't tell you it's 4 10s and 7 1s. But she was able to show in all these different ways that she has that conceptual understanding. Even if you say the number 47 in Japanese, where it is 4 10s and 7, if you don't understand what that means, you still don't have the conceptual understanding. So yes, that's true that the language has some of that built in, but if you don't understand what that visually looks like, if you don't have that representational awareness, then the language calling it that isn't going to boost you up so far. So yeah, there's something to that, but those things are all part of the balanced approach that we use in our math instruction.
We did have a couple pre-submitted questions we can just kind of zip through. We got wanted to talk about. The first one was, will there be weekly or monthly tests to evaluate children for maths and other subjects? And so the answer is there's daily assessments on students. Teachers are constantly assessing students on a daily basis within math and other subjects. Now, as a parent and as an educator, when I look back at my own education and my older children, assessments were those tests where you write it down, you get the answer, and there's a finite answer, and that's where we give a 90% or 100% or 70%, and that's the assessment or test, right? And the shift is that we're always checking on learning. And these are examples where measurements, so that making sure that students understand how objects are measured and what tool would you use to measure different objects. So this might be an activity in class, but the teacher's going around and checking to make sure that students understand measurements. Now, it wasn't a test, but it's an assessment. It's a way in which teacher informs the teacher to know what to do next with the children in her class. And that's happening, or his class, and that's happening all the time throughout the day in all subjects.
I realize we've reached 11 o'clock.
Yeah, your mic is off.
My mic?
No, Leah.
Mine,
Oh.
sorry, I was trying to say something. Since we do need to end, can we push this question to the May one, which is going to be more about how parents can help? I can very quickly say that we do a lot of support within school if a student is showing that they need extra support. And if they're showing they're understanding the math, then we don't need them to keep practicing as they have the understanding already. But we can talk more about this at our May Mustang Connection, since we will be looking at ways that parents can also help their students at home.
Super. Okay. Again, sorry, everybody, we've reached our hour. This was really fascinating for me. I very much enjoyed it. And I'm really happy that I get to sit here and ask inane questions too. So, but you said this is the first, so it's the next Mustang Connection for elementary school in a month. We'll have the second part of this one.
Correct.
Okay.
And if you have questions and you didn't get any chance to ask them, we'll give a lot of time next session so that you can answer and ask questions and get those answers. So please attend, tell others to attend. The more people that can hear this, the more help it can give to their children.
Right. And we've recorded, so we'll put that out to everybody in the elementary school also so that they can hear it. Okay. And don't forget, you don't have to wait a month to ask questions. You can always approach these guys at any time with questions that you may have about things. But thank you very much for your time this morning. Thank you guys. And we will see you at the next Mustang Connection. Bye.
Thank you.
Thank you very much.